Cool, yeah, so I'm David Hall. Until very recently, I was at the Stanford University Center for Research on Foundation Models, where I was the research engineering lead working on Marin. I actually am now at a new nonprofit called Open Athena, which is where I'm also working on Marin, so same stuff. Yeah, I'll start talking about it. So we all use open source, right? Open source underpins everything we do as developers, underpins a lot of the software that we use on our phones. I think it's safe to say that open source software has been a spectacular success. But it wasn't always this way, and it didn't have to be this way. Early on, it started out fairly open. There was the software was shared fairly freely. Hobbyists, researchers would pass code around. But then as things started to get more profitable or get more effective, businesses started to lock things down, and closed source became the norm through the 80s and 90s. But then in the 1990s, we started to see a counter pressure with the open source movement. Things like projects like GNU, Linux, Apache started to take off. And then by the 2000s, I think it was clear that open source has won, at least in infrastructure, DevTools, cloud, and several other places. All right, so AI, right? We all know AI has exploded in capabilities over the last decade, starting with the Sesame Street, Elmo and Bert, way back in 2018, 2017, and culminating today with frontier models like GPT-5. And it's been an explosion of capabilities. We're all here, I think, largely because of how effective these models are. But at the same time that these models have gotten more effective, they've gotten less and less open. So Elmo, Bert were released by, with paper, the code, most of the data, and weights. So you could run the model, you could understand it, you could replicate it. But then by the time we got GPT-2, we were just down to the paper and the weights. The data was never made public, and really the weights were initially withheld as well. And now, of course, we're lucky. With GPT-3, we got a paper, which was great. It was actually filled with a good amount of technical details. But we only got an API. We'll only ever get an API. And nowadays, we get an API and like a tech report that's actually a blog post with archive formatting. And that's kind of the state of AI right now. So the question is, AI, just like software, started out quite open. Then it closed down. Is there some way that we can open it up again? Let's talk about what I mean by open. So we have closed models like GPT-5, Claude, and Gemini, great models. And then we have some open weight models that are powering a lot of startups out there, Llama, DeepSeek, et cetera. And then we have open source models. These are models like early models like GPT-J and also Olmo from AI2. And with open source models, you can see the weights, you can see the code, you can see the data recipe. And then there's also open development, which is where we at Marin are trying to fall on the spectrum. And with open development, our goal is to make it so that not only can you see the weights, the code, and the data, but you can see the entire process, and you can even contribute actively while the models are being trained and while we're doing our work. Okay, so we envision Marin then as an open foundation model lab. But first I want to give you some results to sort of demonstrate that this is actually feasible, that we can actually start to train effective models in the open. So about 4 months ago, we released an 8B model, Marin 8B base, and its performance on 19 different tasks, English tasks, and coding tasks, it actually surpassed Llama 3.1, which of course was the workhorse of the 8B models for the last year or so. And then just last week, we released a 32 billion parameter model. And this model now sits squarely in between the best open weights models that we've been able to find. So it's in between Quinn 2.5 and Gemma's 27B parameter model. Cool. But to do all this, there's a huge design space, right? There's the basics of tokenizers and architectures and losses and such. And then there's all the systems problems of which kernels we need to use, how much parallelism we want to use to maximize throughput. Do we want to train with quantized away training? And then as we're iterating, we have to figure out an experimentation loop that's effective to do things like scaling laws. And then also on top of that, there's the entire data curation pipeline, starting from crawling the web to filtering and rewriting. And finally, of course, there's alignment, RL, and all that fun stuff that everyone's excited about these days. OK, so what does the open source development process look like? These days, we've settled on kind of a fairly sort of tight loop of someone files an issue, and someone puts up a PR that addresses that issue, or maybe they just put up a PR. Maybe you need a couple of PRs to fully address something. But this is sort of the atomic units of open source development, issues and PRs. For model development, it actually looks quite similar. You have a hypothesis that you want to test, and you have a sequence of experiments you run to support that, to test that hypothesis. And so the basic idea is that experiments are really the change lists, the pull requests of empirical machine learning research. And so what we're going to do is we're going to take all of that infrastructure that we as software engineers have developed over the last 10, 20 years and redeploy that for creating foundation models. So an experiment in Marin's sort of view of the world, to start an experiment, you create a GitHub issue, which acts as a form of pre-registration, where you have your idea, you say your hypothesis and what you're trying to test. You put up a pull request that defines an experiment script, which I'll talk about, sort of outlining the steps of your experiment so that everything can be tracked. We have a execution pipeline that comes after that, and then finally everything goes into weights and biases or your favorite tracker for post-analysis and all that. And of course, I'm like 10 minutes into a talk, and at any scale, and I haven't mentioned Ray, Ray fits squarely into this box. And I'll talk a little bit about that later. OK, so to give you an idea of what I mean by an experiment in Marin, let's start with what's the best optimizer for pre-training. One of my colleagues at Stanford, Kaiyue Wen, put up this experiment he wanted to run. It was fantastic pre-training optimizers and where to find them is the title he gave them. And to do that, we just made a little description, a methodology where we said we're going to test this many models at these scales with these hyperparameters. And then from there, we had some hypotheses that we wanted to test. The first was that we expected that a lot of these model optimizers that were supposedly better than Atom actually are really just comparing to a very undertuned version of Atom. And also that, despite that, the matrix-based model optimizers like Muon and SOAP actually should outperform these other methods. And then finally, we get reports that you can click and you can see everything, so you can build upon and learn from our research. And we also put some of the results internally in the GitHub issue. Cool. So just to dive in a little bit more into this issue or into this experiment, we tested 11 different optimizers, starting with Atom W as the baseline, looking at a bunch of these Atom sort of variants, and then looking at the memory efficient optimizers like Lion, as well as matrix-based optimizers like Muon and SOAP. And sure enough, it turns out that the reason why most of these optimizers appear to work in papers but don't work in practice is that the baselines have been drastically undertuned. With just a slight tuning of the learning rate for Atom W, you can get a 2x speed up, which more than erases the gains of some of the other optimizers that have been published. That said, we do see that optimizers like Muon and SOAP actually do seem to have gains that persist with scale, both in terms of model size and in terms of like number of tokens. OK, so that's an experiment. Or that's an experiment. Let's talk about like how we represent experiments in Marin. So the basic idea is that we represent experiments as a data flow graph, where each stage in the pipeline describes an atomic unit of work that needs to get done, that produces some result, and then you can build upon those results through by connecting the nodes in the graph. So in this graph, we want to say tokenize this pre-training corpus called DCLM, evaluate on Paloma during our training so we can monitor how our performance is going. And then we can start actually training our model. Once we've trained that model, we can then fine-tune the model on, say, Tulu v3, and then we can evaluate the model on MMLU and a suite of evaluations. Okay, so operationally what that looks like is a Python script. So Marin captures the entire experiment as a data flow graph written in Python, like we see here. And we provide a library of sensible defaults that provide strong baselines for individual components. So common data sets and defaults are extracted, so you can just import them and use them. First, this slightly simplified script on the right represents a sort of replication of NanoChat, which is Andre Karpathy's sort of most recent project, where we train a very small model on a decent amount of data. We then chat tune it, and then we can actually talk to it. Okay, and so to do this, to train this model, we just import some data sets. Say we're going to train a model we're going to call Merino Chat, and then do some fine tuning. Note that steps can depend upon other steps, and they'll block execution until they're ready. So you can fire this off to Ray, and it'll schedule things correctly, blocking until things are ready. And finally, you can dispatch the steps to the executor, which will crawl the dependency graph and execute things as is appropriate. Cool. So that's a toy, right? A 350 million parameter model that runs on a single machine in a few hours. But we can do much larger scale things. So here's a script that trains an entire isoflop suite that runs about 200 different models, or trains about 200 different models up to 10 to the 20 flops. All from a single file. And similarly, entire multi-month, multi-step runs can be specified from a single script. And all of our runs are done this way. Okay, so let's talk a little bit conceptually about how the executor works. The basic idea is that we have our pipeline graph. And each one of these nodes, these bubbles, are Ray tasks. They get scheduled. They might dispatch to other Ray tasks, but there's sort of a controller task that sits at the top of each one of these. And we create a hash of the inputs to every node, as well as the sort of core, the critical hyperparameters that would influence the outcome of the model training. And so everything gets a hash. And so if you want to run an experiment, you can easily get careful controls. For instance, if you wanted to say, what if I use my new SFT data set? I can plug that into this pipeline, and I will immediately it'll change the hashes automatically, retrain just the pieces it needs to train, and then you can have a tight, carefully controlled experiment and get the results. Okay. I'm going to talk a little bit about the 32B model that we trained and how we used our pipeline to sort of handle not just the initial training, but also debugging all of the various things that came up on the way. Okay, so Marin 32B started out very similar to our 8B model that ran. We used this NVIDIA's Nematron CC dataset that's a very high quality web text dataset. StarCoder is a high-quality coding data set that we used, and ProofPile was one of the best math data sets that was available at the time. And we started with a Llama-style architecture with about 32 billion parameters. And the script, slightly simplified, basically looked like this, where we say, give us Nematron, give me ProofPile, give me StarCoder, put them all in a mixture, and then train the model. and everything goes, that's all we really had to do to kick off training. So we started training, and if you're used to looking at loss curves, you might get a little afraid of what you're seeing. They start off extremely spiky, and we were a little hesitant, a little concerned about the spikes, but we thought maybe things would be okay because our model was basically recovering from the spikes pretty quickly most of the time. And our sort of comparison runs, we were running way ahead of our comparison runs. So this line here is the 32B, and you can see that it's doing much, much better than all of our other runs matched for compute, even better than a 70B test run that we had done before. So we were feeling nervous but cautiously optimistic. But then something happened that was pretty bad. We got hit by what we call the bad spike, where the loss went up. Not that much compared to some of our other spikes, but it never came back down. And something just went sort of fundamentally wrong. Something got seared into the parameters that the model wasn't able to recover from. So then we decided to do a whole bunch of necromancy. So we tried a whole bunch of different things. We decided to skip some of the bad steps that were happening right before the bad spike. We tried clipping the gradient norm to be tighter. We noticed that gradient norms typically need to be, are typically less than about 0.2 for this model. And so spikes tended to be around the time when the gradient norm would explode. And then we also tried clipping the update norm, clipping how big of a step the optimizer was allowed to take. And we even tried muon based on the success that we saw in that paper. Unfortunately, none of these things worked. So the necromancy made the loss be about the same. It didn't really change anything at all. And muon looked great. It's the red line. And but then eventually decided to just kind of like go to space. And we aren't totally sure what we did wrong, but we will keep investigating. But we persisted, and we tried adding QK norm, which is known to stabilize these models. It's been used by many models, including Quinn, for stability. And we didn't want to add it in part because we didn't need it at 8B or 70B with our prior runs. And also there's rumors / some evidence that it has negative implications for long context extension, and we didn't want to foreclose the ability of our model to be good at long context. But at this point, we didn't really have a choice. So we warm started our checkpoint from the last good checkpoint that we had from the 32B. Piped it into the model with the new Quinn data set, or the Quinn model, sorry, and started training again. And then after a very brief spike where the model had to recalibrate starting from these sort of very different architecture, or somewhat different architecture, the model caught up after about 10 billion tokens catching up to where the model had been. So the sort of problem was patched fairly quickly. And then after that, everything was smooth for the rest of training. So QK norm is good. Okay. Finally, it was time to do a cooldown mix. So in these days, what people do when they're pre-training a model is they actually take their best data, and they push it to the end of training. This is called mid-training. And we followed sort of a fairly standard procedure where we take all of our high quality data, which includes things like Stack Exchange, Wikipedia, some various question answering data that we found, and we mix that 70-30 with the original background data set. And then we started learning rate cooldown at the same time. And things look great. Our losses went down very fast. A lot of this is just purely due to the cooldown, but we saw specific gains on particular eval data sets looking at code and other stuff like that. So it was a solid cooldown. And then, as I teased earlier, the model actually performed quite well. We ran it on 19 different benchmarks, and it kind of sits in between Quinn and Gemma in terms of performance. Okay. So Let's talk a little bit about our infrastructure and how Ray interacts with it. So Marin is mainly powered by Google's TPU Research Cloud. Because we are a university and now a nonprofit, they give us access to TPUs for free. And in exchange, we say nice things about Google. Google TPUs are actually very great. But most of our compute is preemptible, right? Google, gives us TPUs, but they kind of would rather paying customers use it for obvious reasons. So we have all of these TPUs that we can use for a couple hours, maybe a couple days, maybe it's 20 minutes. And so nodes are constantly being disconnected and recreated by Ray. Or by Google, and Ray allows us to monitor and provision new nodes to the cluster. It knows how to allocate TPUs, but TPUs come with a few wrinkles. So for those of you who don't know, TPUs are kind of like GPUs, only more so. The basic idea is that, and the thing that really distinguishes them is that they are tightly interconnected via this ICI mesh, where they have these very high performance interconnects in between them. And they also are each sort of group of 4 TPUs is controlled by a VM. And all of these VMs need to be computing the exact same, or need to be running the exact same kernels on all of the TPUs at the exact same time. This is actually something that's a little bit of a challenge for Ray. Because while Ray has the ability to launch, provision, and monitor TPU slices, it doesn't actually have the ability to schedule more than one TPU VM in a coordinated way. It doesn't have any kind of gang scheduling with cross-host dependencies at all. So for instance, if you were a GPU shop and you said, give me 8 DGX boxes that are on the same InfiniBand switch, Ray doesn't have any mechanism for helping you out with this. There is a trick though, and we expose a simple API that makes it about as ergonomic to use TPUs with Ray as it is to just do ray.remote. It handles the gang scheduling, it handles the retries, it handles coordinating multiple TPU slices together. It was based on some work that Alan Wang, who was at Google at the time, is now at Meta, put together. And the basic idea of how it works is that Ray already allocates provisions nodes with a couple of special resources. So for a TPU VM, not only do you get 4 TPUs per VM, you also get a little marker indicating the name of the TPU slice that Ray or Google assigned to the TPU slice. And then the 0th VM also gets the special TPU type of TPU slice head node. And you might be saying that 4 times 4 is not 32, and that is true. But Google pretends that this is 32 TPUs. So how do we do this then? The trick is, so if we have a Marin step that wants to use a TPU slice, we invoke Ray TPU, which has a nominal amount of CPU, and that creates a slice actor. And that slice actor, we say, needs to consume the v432 head resource. That means it gets placed on one of these VMs. And once we're there, we can get the slice name that we're on. We can then create the number of TPU VMs that we need to, we can create a number of actors equal to the number of VMs we need to schedule on. And then we can actually run the payload on those host actors. So basically the idea is that the TPU v432 head acts as a kind of semaphore. Once we get a lock on a particular TPU head worker, it's easy to get the slice name and then schedule the end tasks that actually do the work. Okay, preemption is easy to handle as well. So if a slice goes out, typically what happens is that only one of these will fail initially in our experience. But we can kill the whole thing, retry, and then start over. It works kind of more or less the way you would expect. And then finally, on this note, TPUs have this really cool feature called multi-slice. This is where you can coordinate multiple groups of TPUs that are not connected by this tight ICI connection, but are instead coordinated over the data center network. And you can link them together and sort of schedule training over them, doing things like hybrid sharded data parallel training. And this is really good for us in particular because we're using preemptible compute. So we want to use lots of little small slices because it's easier to fit in the cracks. And so all we have to do is pass some magic environment variables to JAX, and everything will get handled for us. And under the hood, what this looks like from our perspective is we just make a slice actor for each TPU head, and then everything continues, and it works great. OK, finishing up, I want to talk a little bit about the community. So like I said, Marin's an open source, open development thing. You can come participate with us. We do most of our coordination over Discord. There'll be a QR code in a little bit where we're talking about our results as they come in, debugging things as they come in. So if you want to learn about pre-training, you want to learn about fine-tuning, you want to learn about data curation, we are working on that, all of that in the open. We even have initiated some community projects. So in the next day or two, an 8 billion parameter multilingual version of our 8 billion parameter model will be finishing. And this was entirely started by members of the community. They found the data, they found the evals. All we did was kick off the run and have been monitoring it. So in conclusion, Marin is an effort and a framework to develop an open foundation lab. We use Ray, it's great. You should join us. And let's build the Linux foundation models together. Thanks.
Thank you. That was a great talk, David. Any questions? Don't be shy. There you go.
Fantastic talk. What do you think of the open MDW license from Linux Foundation and that approach to publish models?
I don't have strong opinions about it. I think we used it for the most recent thing. It seems like it's the obvious Apache equivalent, and so it seems like a good license.
Hi, thanks for the talk. I was actually curious. So you mentioned that like both the recipe and everything is open source. Let's say if someone wants to know like kind of how much compute was required overall for the 32B or the 8B run, that would be inferable via VanDB, which is public, or there would be something else needed?
Yeah, the 1B is all public. So you can go in and see how long it took and how often we accidentally let the run die. Yeah, so you can all see it all, and if you want to just see like how many model flops were used and the theoretical flops, it's all there too, of course.
Hi, David. Great talk. So I have a question about the open source community. What's your strategy to allocate the computer resources? I know it's kind of provided by Google, but the resources still limited. What's your strategy here, especially for the pre-training?
Yeah, it's a great question, and we're still trying to figure out exactly how we want to do this. We obviously can't give direct access to our compute because you can run up really high bills. But part of how we think about this is that preemptible compute is hard to use. TPUs are fairly not nearly as well known how to use them outside of a couple of very large companies. And so what we're trying to do is provide the framework and the expertise so that when people come and want to train something, we can help them out. We're probably going to kick off some runs around safety pre-training, so like data filtering stuff to make sure that the model can't spit out stuff about bioweapons and things like that.
Sorry, I have a follow-up question. So what's your strategy here about the license data? Data
licensing?
Yes.
Yeah, it's a great question. We obviously, because we're doing everything in the open, we're not going to be able to do what allegedly some other organizations have done and download, torrents of all of the academic papers that have been published and books and stuff. And so we rely instead on data that's sort of broadly available. That includes Common Crawl and all that. We do need to figure out the best way to remove sort of sensitively copyrighted data from that, but we're working on that.
Thank you.
Thanks.
That's all we have time for. Thank you, David, for all this community work that you're doing. It's great. Thank you, everybody, for attending.